Overstating it a little bit. So I've, for a long time, been very interested in automatic theorem proving and had a sort of strong conviction that fully automatic theorem proving ought to be able to do a lot more than it can do now. I'm not making any claims to having a system that can already do this sort of thing. I just want to try to sort of justify in a non-formal way, or sort of just defend to some extent my optimism in this direction by just giving various examples of things that sort of seem difficult and seem to require a magic idea or vast amounts of computer search, but actually when a human mathematician does them, somehow we sort of find our way through this enormous thicket of sort of tempting, I'm mixing my metaphors terribly, sort of tempting wrong turns and so on. And I think the best I can do, I have thought quite a lot about the sort of privately, so to speak. So what I'm doing is telling you my private thoughts rather than my sort of things that are worthy of turning into a paper and publishing, that sort of thing. Although I hope that they will develop into something like that, but I don't claim to be ready to take that step. So what I want to do is really focus on a few examples and then just comment on those examples as I go through them, just to give the sort of flavour of the kind of thing that I'm trying to do. And it won't be a complete account of everything that I've tried to do, but it certainly gives some idea. And in order to do that, it's necessary to discuss problems of all sorts of different levels of difficulty, because somehow it seems that the general problem, how do we do mathematics, itself involves problems of lots of different levels of difficulty, sort of from very routine things that we do easily, but sometimes computers still find quite difficult, to the kind of problem that you just stare at and think, I have absolutely no idea where to start, and then you sort of think for a little longer, and you finally find some way in, and what is that process of finding a way in, and so on. Some of the things that I'll be talking about, particularly on the sort of lower level things, are ideas that I've not had in isolation, largely in conversation with Mohan Ganisaling, with whom I have one paper in this area, my sole publication in the area of automatic theorem proving, and more recently Ed Ayers, that some of you will have heard talking about interfaces, who I'm supervising him with Mateja Jamnik from the Computer Lab, and I hope that he and I will be able to develop at least some of the sorts of things I'm talking about, but not the more ambitious ones. It'll be clear that some of them are much more ambitious than others. So the really ambitious ones are things where I feel, so a rough picture is, for the ambitious ones, that I have sort of high-level ideas for how we manage to reduce the search, but in order to implement those, you need to get the low-level stuff sorted out as well. So I'm sort of hoping, and maybe this is where, maybe that'd be a sort of, because I feel that most of the sort of things I've heard in the workshop are more to do with the low-level thing, but I think there's some value in trying to think hard about the high-level things, in the hope that at some point the low-level and high-level things can meet in the middle somewhere, and so if we can sort of fully automate fairly simple problems, then we can sort of use that as a stepping stone to much more interesting things. So what I plan to do is just, as I say, go through various examples and discuss the difference between how a sort of slightly naive machine algorithm might do them and how a human mathematician would do them, and why the human mathematician, how and why the human mathematician reduces the search. So the first example I want to talk about is one that came up in a paper by someone whose name I've forgotten, I'm afraid. It's a sort of German name. But the problem was to show that if you've got a group such that actually I can't remember what the initial problem was, but the problem that I want to talk about was not the initial problem. The problem that I want to talk about is something that you could quickly reduce the initial problem to after you had explored one particular. So the way you did it, you sort of did a few steps, and then you had to choose a value for a certain variable. And if you chose, there were sort of two obvious possibilities for what that variable would be, and you had to decide which was the better one. And the first one led to wanting the following to be true in all groups. You wanted the statement x to the minus 1 equals x to be true in all groups. And the way the program tackled this, of course it didn't assume that it was true, and before trying to prove it, it said, okay, I'm going to test this against a small bank of examples of groups. And one of those groups was, I think, the Klein group. I'm pretty sure that was the one the program used for this equation, so it sort of picked an element of the Klein group and discovered, or maybe it searched through all the elements of the Klein group, and perhaps starting with the identity, who knows, but anyway, eventually discovered that there was an element for which this equation was false in that model, and therefore this equation can't be universally true. And it's very clear that there are sort of a few things that a human mathematician would not like about that way of doing things. So one is, when I look at this, it's just completely, totally obvious that that's not true in all groups. But it's not good enough just to say something's completely obvious. You have to say, well, if something's obvious? A former colleague of mine had a great slogan that a statement is obvious if a proof instantly springs to mind. So what is the proof? Well, you might say that the way to disprove something like that is to come up with a counterexample. So that, in a way, that program seemed to be doing a reasonable thing. But that's not what a human mathematician would do. I think a human mathematician would immediately say, if x to the minus 1 equals x, then x to the minus 1 is the identity by the cancellation law. So we wouldn't just say, here's a statement that we want to disprove, let's try to disprove that statement. You do a bit of reasoning. So there's a very obvious piece of reasoning, and in fact, it's an equivalence. So we just say, well, let's reduce it to a simpler looking statement. Now once we got into this statement, we say, is there a group such that there's an element with an inverse that isn't the identity? So this is where we get, I think perhaps I ought not to discuss this too much. I've reduced the problem to a sort of lower level problem, which is easier. But anyway, any group with more than one element, so it's not quite as simple. If I'd started x to the minus 1, x equals x to the minus 1, which is I think what I intended to start with actually, then I'd be left with x equals the identity. So I just have to find a group where the identity is not the only element, and then it's easy to see, well, we need the group to have cardinality greater than 1, and that'll be sufficient, because if it's only got the identity. Or perhaps we can even say, supposing this were false, what could we deduce? Supposing it were false that this wasn't always true. In other words, suppose this were always true, then we would have that there was only ever one inverse in any group. And there's a little bit of extra reasoning because of this minus 1. And that sort of thing is, I don't deny the existence of those sorts of problems. This minus 1 sort of throws, not a human being, but it throws the computer ever so slightly if you're trying to program it. But I think that's a problem one can sort out. The main thing I want to point out is just the program that we looked at, or the paper that Mohan, Ganisalingham and I found, had this thing where just whatever the thing was that you wanted to find a counterexample, you just test it against a bank of things as the statement was, and that's not how a human being operates. A human will do a bit of reasoning and end up with something usually rather simpler to do, and in that way reduce the search. So now we've reduced the search just to basically find a group that isn't the trivial group, and such things are. Then maybe you do look at a bank of examples, but you really don't have to search very far. So what was my second example? Again, I'm not going to analyze all these in total, but here's a problem that appears on undergraduate example sheets sometimes. So supposing you know that K is a normal subgroup of H, and H is a normal subgroup of G, does it follow that K is a normal subgroup of G? And so how would a human tackle a problem like that? Well, I think a natural thing, especially an undergraduate might well think, well, it's quite plausible that is a normal subgroup of is a transitive relation. So let's just sit down and try to prove it. So we'll say, so we're assuming all this, let's take an element of K and try to show that if you conjugate it by something in G, you'll get something in K again. So we take our G belonging to K, let's not call it G, I'll call it little k, and we'll conjugate it by some arbitrary element of G. And then I think a typical human mathematician would look at that and say, I've got absolutely no reason. There's nothing I can do with that expression, given the assumptions I've got here. Perhaps that's not quite true. Perhaps you could try cleverly to express G as a product of something in H with something else, but why would that help? I don't know. It's not obvious. So at that point, you might think, okay, so the sort of sit down and do the obvious thing has failed, so it's probably false. And this is another way that we reduce search. So when you're trying to solve a problem, there are lots of things, usually lots of things that you can try. And one of the things you like to try is you generate statements that might or might not be true, and you try to prove them. But sometimes it's an effort to try, well, it's always an effort to try to prove a statement. So if you've got a choice of sort of 5 things that you might consider trying to prove, then you don't want just to say, let's start with number 1, as a computer might do, have a go at that, and then if I get stuck, I'll go for number 2 and try and prove. That's just not the way a human will work. A human will look and say, they'll do a sort of cost-benefit analysis. Are there any here that are not likely to be that much effort, and also are likely to lead to a reward? And one way you don't get a reward is if you try to prove something false. So this process here is actually very important. It's not a complete waste of time, because it increases our confidence that this statement is false, and that the right thing to do is to search for a counterexample rather than a proof. It changes the cost-benefit analysis when a sort of easy method of trying to find a proof has got stuck immediately. Anyway, we don't stop at that point, though. So we say, now it seems as though we've got a huge search to do. We've got a vast space of groups and subgroups, and sort of which one will we choose? Should we just start with the smallest group and build up, again, as a computer might do? A human would never do that. They would start saying, well, if we've got a counterexample, and this is a very, very general thing you'll notice I'm saying, if you've got a counterexample, can we say anything about that counterexample? And there are some very simple things that we can say about the counterexample, such as G can't be abelian, because if G is abelian, every subgroup is normal. So it can't be a counterexample. So it immediately says it's going to have order at least 6. Supposing we then think, okay, well, we only know one non-abelian group of order 6, because there is only one. So also, all the subgroups are going to have to be proper. So if we start with a group of order 6, has it got any? I mean, start with the symmetry group of the triangle. That's the one that we're taking. Have we got a proper subgroup that's normal? Yes, we have. We've got the rotations. But unfortunately, the rotations don't have any non-trivial subgroups, because it's a cyclic group of order 3. So that's too small. And it's also given us an extra. So looking at this example has given us an extra thing to think about when looking for other examples. We would like to have a group that has a subgroup that has a non-trivial subgroup. That's an essential thing. Actually, it doesn't really, in this particular case, change things too much, because if we just carried on, 7 is obviously hopeless, 8, and in fact 8, once you get to 8, you can find groups that have subgroups that have non-trivial subgroups. Anyway, so now without really sort of doing much searching, we've got ourselves to a situation where we are looking for, it's a sort of natural thing to do, to look for a non-abelian group of order 8. And there are a couple of natural candidates. So one is the quaternion group Q, and the other is the dihedral group of order 8, or symmetries of a square. And actually, just one of the things I did to prepare for this talk was actually to do some problems. And so with one of these, I'd forgotten which one of these was the one that worked. So I tried the quaternions and then quickly found that it didn't work, because if you take, so the obvious subgroup to take is the one generated by 1 and I, minus 1 and I, which gives you 1 minus 1 I and minus I, which is cyclic, and because it's cyclic, well, it then has the subgroup that consists of 1 and minus 1, which is normal in the whole group, which is annoying. So that one didn't work. And there I have to confess that I used some search. So I don't deny that humans do use search. They just use much less of it than naive computer programs. And then D8, well, it's not that hard to find an example. Although actually here, one can sort of even here we can think, how are we going to prove that the subgroups are normal? And if you know a little bit of group theory, then you realize that the only possible orders of these subgroups, by the way, by Lagrange's theorem, are 8, 4, and 2. So then suddenly, if you know a bit of group theory, you think, oh, well, that's fantastic, because actually then H is a subgroup of G of index 2, so automatically normal, whatever we end up choosing, and K is a subgroup of H of index 2, so it's automatically going to be normal. So all we have to do now, notice I didn't sort of test various subgroups, I just did a bit more reasoning and worked out that all I need to do is find a subgroup of D8 of order 2 that is not normal. And then if you have any sort of understanding of what a normal subgroup is, you'll know that if you just take the subgroup generated by a reflection, it can't possibly be normal, because if you conjugate it by a rotation, you'll get a reflection in another axis. So this combination of looking for examples and doing reasoning is what leads us quickly to a solution, rather than sort of, if you're programming, it's very, very tempting just to say, well, let's now go off to our library that's got huge numbers of things. And I should just quickly say, even though I think it's fairly obvious, why it is that, well, why I'm so anti-search, and why I think it's a good thing to be anti-search, and why I think it's a very important part of how humans do mathematics that are anti-search. And it's just simply because when you're trying to solve a problem, it's a very hierarchical process. So you sort of say, I want to prove this statement, I have no idea how to do it. Here's another question I might tackle, I have no idea how to do that. So let's try this one, and then this one, and then you end a big sort of, it's not just one question I wanted to ask to help me with this, there are all sorts of questions. And if you've got to start getting a tree, and at each node of the tree you've got quite a big search, then you get a combinatorial explosion extremely quickly. So you somehow have to find ways of course, cutting down search is something that all automatic theorem provers do. That's a sort of huge part of it. So what I'm saying is not that different, but I'm just saying that I think that humans, because our brain, we don't have the processing power of a computer. We go much, much further than a lot of programs. We don't sort of say, I'll start with a brute force search. Oh, bother, that's going to take me 2 years on my high-performance computer. I'll have to cut down the search a little bit. And then when you finally got it down to 2 weeks, you say, OK, now I'll just run it for 2 weeks and I'm happy. A human being will not be happy with that. They have to go much, much further. Of course, that means that humans won't be able to do everything that computers can do, and we know that very well, especially after the last week or two. But there are other. I also think that part of the reason that humans outperform computers in many problems is precisely because of cutting down the search to almost nothing in many cases. Okay, so that was my second example. So my third example, slightly different flavor, but it again involves a construction. And I'm not going to go through the whole. It starts with the following problem, which is a standard fact in an undergraduate course on topological spaces, which is, I'm not going to talk about this problem. I'm going to talk about something that comes towards the end when you're writing out a proof. So it's a compact subset of a Hausdorff topological space is closed. Maybe I'll just say verbally what the proof is, but if you don't follow that, it doesn't matter. So the rough idea is you have your set Y, you have an element X here, and because it's Hausdorff, you say that for every Y in Y, you can find an open set about X, which I'll draw fairly generally. That's UY, and an open set about Y, which I'll call VY, and they're disjoint. So that's what you get from the Hausdorff condition. You can ask yourself, why would a computer think of doing it this way? Well, I have answers to those sorts of things, but that's just not the part of the argument that I want to focus on. So let me just write down when you've got to that stage. Then we apply compactness. So we've got these sets Vy for every Y in Y. So their union contains, perhaps I could have drawn this one. Some of them could be outside Y. their union contains y, so by compactness there's a finite subcover. So when you've got that, we have the following situation. We have, for all y in y, so we have some open sets. So x is in uy, y is in vy, uy, vy open, uy intersect vy is empty, and yes, that's what we've got. And then we apply compactness, and we find y1 up to yn such that capital Y is a subset of vy1 up to vyn. So that's all our sort of data. And what is it that we want to prove? We want to prove that u star intersect y is empty, u star is open. I'll tell you what u star is in a minute, and x is in u star, or rather I won't tell you what u star is, because u star is something that we want to find. It's an object that we want to find. Now if you're lecturing a proof like this, you don't say u star, you just say, let's take the intersection of the uyi's from 1 to n and check that it works. But that's something where, if you try to program it, that's a sort of rabbit out of a hat, and if you try to program a computer to come up with rabbits out of a hat, it's going to have to try an awful lot of rabbits before it gets one that actually does what it's supposed to do. Let me put a line here to distinguish between what we know and what we would like. But that sort of at first seems like a big problem. You've got to have this sort of inspired idea to choose u to be the intersection of the uyi's that correspond to these vy's. How on earth are we going to have that idea? I beg one?
Place the vy's by their closures.
There are probably all sorts of things we could do. Yeah, so that is one way that one could do things that then prove that the complements of the closures contain the ui's and but again, this may not be true, but that sort of felt like another rabbit out of a hat sort of thing. So so the existence of other ways of looking at things, I'm not claiming what I'm doing is the unique way of looking at things. I just want to show how one could hope that some program that doesn't yet exist, but I feel is within reach, could come up with a suitable candidate for u star. It won't be precisely that one, although I think one could imagine sort of feeding it with slightly different data so that it might hope to come up with an idea like that as well. So, but that's something I'd have to think about to get clearer about it. So
I think, what's interesting in both your examples is you're exposing your thought process to us, and your thought process always involves a visual picture.
Yeah, so that's something I was...
And the undergraduate might, when he's got the y into yn, actually sort of draw about 5 or 6 and then see, oh yes, look, we can just, that means the things that are in common to the VIs don't meet any of there may be...
Yeah, so I was going to say that, or something similar. So we might, we have pictures like this. When we're doing examples in topological spaces, we sort of, our mental topological spaces often just are squared. And for many purposes, that, an example I was discussing actually the other day with Ed and Bohar was how to show that a metric space is Hausdorff. And, you know, that's just something that is incredibly easy because you say, let's take 2 different points. Okay, I'll just proof. And now let's just convert that, you know, it's a slightly tedious process to, and that's actually problematic because, well, it's just, this is something I definitely, this is one of the things that sort of puts a check on my optimism, the fact that we do so many thoughts like that, and those really do seem quite hard. I mean, I don't think it's necessarily totally impossible to model that sort of thought, but I don't have good ideas.
Could imagine, as it were, building up computers.
Sort of library of known fact.
World in those terms. I mean.
Yeah, I think it would. Right, but that would be a sort of quite a big task. And I think what I'm about to show is simpler than doing that, even though it would be very, very interesting if one could somehow encode visual facts in a computer-friendly way. So what I'm going to suggest is a technique that works for a lot of existence problems, and it's not a universal, it's not a panacea, but it does work in a lot of cases and reduces what initially seems like a kind of infinite search space and all the open sets there might be. Of course, actually it's not really infinite because we're restricted to open sets that we could define in terms of the objects we've got around, and that's rather more of a finite thing. But let me just, so this technique is you just, you take U, I mean, there's the term used in automatic theorem proving, as people here will know better than I do, meta variables. So we sort of, this star is indicating that U is a meta variable. So what you do is you say, I don't really know what U is yet, so I'm just going to go ahead and try and prove that it works. And this unknown open set. And when I find, this is the technique, when I find that there are facts about U that I need to be true, I'll just sort of add those as things that I want. And the hope is that by the end I'll have got a bunch of facts that I need U to satisfy, and that finding U to satisfy those facts is much easier than finding U to satisfy these facts. That's the sort of rough idea, and I'll just show you it works very easily in this case. So how do we show that? So, oh yes, the other thing is that you often get in existence problems, you get a sort of, you want to show three things are the case, and sort of showing three things at once is a bit of a challenge. If you've just got one thing to show, it's okay, but if you've got three, that can be problematic. And humans, I think, use a bit of judgment here, and they say, well, which is the one that I should focus on at this point? Which feels like the, I'm not sure I can come up with a really good answer, except in this case, except that my instinct as a human is very strongly that this is just a sort of type condition almost, so not something that I sort of think about too hard. This looks like a very simple statement, but this is the one this is the sort of killer. This is the thing that's the real challenge, getting my set to be disjoint. So let's focus on how the proof of disjointness will go. So how do you prove that something's disjoint? From another set, we'll say, let X be in this. I want to prove that it's not in this. So I'll just, let's get rid of that. Let's try not to take too long here, because I've got some significantly harder problems to discuss. So, so X is in U, that's our piece of data together with the data up there, and so X is in, yes, X is in U star, and I want to call it U, sorry, thank you, yeah, and U not in Y. So how are we going to prove that U is not in Y? We don't know much about U star. In fact, we know nothing at all about U star. So forwards reasoning from this hypothesis is a little bit hopeless. But we could try backwards reasoning from the target, U not in Y. So is there anything that would help us show that U is not in Y? Well, there's only one thing that we really know about Y, which is this statement here. And we see that that does help us quite easily with backwards reasoning. We can sort of get rid of that target. I'm tempted to rub it out, but I want to sort of leave, so I'll get a different, no. Okay, so here's my sort of temporary notation, double backslash. That means that's not the target anymore, but I'm leaving it there so you can remember what it was. So the new target is U not in VY1. Of course, there are questions about how exactly, what are the mechanics of deciding to replace the target, but that's a lower level problem than the one I'm talking about, really. All right, so how do we prove that? Well, not to be in a union is equivalent to not being in any of the sets. So new target for all I from 1 to n, U does not belong to VYI. And then we do the sort of, let's pick an arbitrary I, so get rid of that. So we've got that U is in U star. We want to prove that U is not in VYI. We can carry on with the backwards reasoning because we know that UYI intersect VYI is empty. So it's enough to prove that U belongs to UYI. And so now we've got, now that this is a sort of possibly the main reason that I don't, Mohan and I never actually got our program to the state of being able to solve this problem fully automatically. It's because there's this stupid sort of, it should be easy once we've finally thought about it enough. But what we've taken this process of starting with for all I, getting rid of it by, I've forgotten the technical term for it, we called it peeling the quantifier, but getting rid of the for all, so that we're looking at a particular I, but now we want to put it back in again at this stage. And mostly you don't want to put it back in, and so how do you decide when you want to put it back in and so on? That's an annoying little sort of technical problem. But I don't think it's a genuinely hard problem. We put it back in. So we've got that u belonging to u star needs to imply that for all I, u is in u, y, I. Well, that statement is equivalent, and it's a good equivalence to use because we'd like it to be in the form u belongs to some set. So that target can be replaced by u belongs to the intersection I equals 1 to n, u, y, I. And now we've got a fairly simple looking problem. Can we find a u star such that u in u star implies that u is in the intersection of the u, y, i's? And obviously we can. So by just doing backwards reasoning instead of, we didn't actually ever have to think about what u star would be. We just did all the obvious backward steps, and the set just popped out. And thereafter, you just have to check that it's open, that it's an intersection of finitely many open sets, and so on, and that it's disjoint, and so on. Sorry, the disjointness comes more or less automatically, but what was the other one? Oh, that x belongs to it, and that's also easy to check. So again, the same sort of message as the first very simple example, that if you do a bit of reasoning, you can end up with something much easier. So you did a bit of reasoning before coming up with the example that was the counterexample. Here again, we've done a bit of reasoning, and then the set that will make the proof work is something that's very easy to find. What was my... Okay, so now we jump from sort of routine undergraduate exercises and proofs to something very different, because so this is where I'm talking about something that's not going to happen in the near future, but that I do think will happen eventually, and will sort of happen when all these lower level things get properly sorted out, which may take a long time, but not a sort of infinite amount of time. It's not. I really don't believe that we have some sort of magic source in our brains that computers are never going to be able to have, with the possible slight exception of this visual way of seeing things, which I think, I don't know how essential. I hope it's not too essential. Yes?
So Tim, can I ask a question now, because I need to leave the room soon. Do you think that there is a point in time that we'll be able to teach computers to be intuitive about saying, so for them to look at the pieces of ammunition that they've got from the information they know and say, in this instance, I need to start at the bottom rather than starting at the top. So do you think that is actually almost a counting exercise? Look at the piece of ammunition you've got and what's most likely to be tractable on what you're working with. So we look at it and we go, obviously, I can't do anything with the u as an element of u star, so I'm going to start at the other end.
I see what you mean, yes.
Is it obvious to a computer by a counting algorithm, is what I'm trying to say?
I'm not sure you need a counting algorithm for that. I think you just need some sort of algorithm that's got... so the algorithm that Mohan and I developed was what's called a waterfall, has a sort of waterfall architecture, where you have a bunch of things you can do, and you just pick the first one that can be applied, and then the sort of art of programming it is to choose a good order so that it mimics the way humans do it. So there, if you've got a waterfall architecture, I'm not saying you have to have a waterfall architecture, but if you do, then you might just say forwards reasoning from the hypothesis is an available option, but when we try and do it, there isn't anything, so it moves on to the next thing. That actually, I have to admit, is not 100% human. You could regard a waterfall architecture as a sort of search, because it's looking through a number of possibilities, some of which a human would obviously know in advance are not going to work. But there, I think, somehow the amount of search is very clearly bounded in that case, because you just go through a bounded list of sort of 15 things to try, and that's not a huge... that doesn't really count as that's not the sort of search that's going to lead to a combinatorial explosion. But for more complicated things, I mean, it really is the case that when you've got a difficult problem and there are things that you might try, here's another situation where it's not necessarily going to be easy. I would absolutely realize this. That you make judgments of what's likely to be hard and what's not likely to be hard and that kind of thing. So if I could try that, expanding out that polynomial, but it looks nasty, or that sort of, or those sorts of things. And actually, it's with those kinds of judgments. I'll say this in a heavily qualified way, but with those kinds of judgments, I think machine learning could have a role to play. But my feeling about machine learning, just quickly, is that it should come in not at the beginning of the process, but only when you've sort of got to those bits that are slightly less easy to sort of automate. You know, you do as much reasoning as you can, and only when you get to a sort of delicate judgment might you think of putting machine learning in. But that's a sort of aside. I don't mind talking about that a little bit later if anyone wants to challenge what I just said, which is entirely reasonable reaction. Anyway, so the next problem that I wanted to discuss is the following. So I'm going to leap from routine-ish problems to Olympiad-style problems. So one I'm going to talk about is one I've talked about a couple of times before, so I hope, apologies if anyone's seen me talk about this. Actually, Joe Corneli, I think, may have mentioned it in his talk, but I don't think he would have. If you went to his talk, you might have seen a rather nice diagram. So what I'm going to talk about is, I'm sure he wouldn't have gone into the actual thing in the sort of detail that I'll go in now. So here's what it is. And then after that, I want to talk about something that's sort of totally fresh. I'm going to France for a year next year, and in the process of clearing out the house to make it suitable to rent. And it's a huge thing. It's part of the reason I had to arrange this at such late notice. And while doing so, I found an old copy of The Emissary, which is the sort of magazine put out by the MSRI and sent to anyone who's ever been to a program there. I don't know why I'd never thrown it away, but anyway, I was flicking through it to try and find out why I hadn't thrown it away. And I came to a page that had some problems on it. And I thought that looks just like the sort of problem that I should talk about. And it turned out that it had once been on an American Maths Olympiad paper, and so I thought, well, slightly nervously, I thought, okay, well, I'll see if I can do that this morning. And fortunately, I'm pretty sure it came out. It came out unless I'd made some stupid mistake, and if I have, it doesn't matter, because at least I'd sort of talk about the thought processes. But this one is less fresh. This is something I was shown when I was at school. But when I was shown it at school, I think I was told the answer, and it sort of looked like a sort of piece of magic that nobody could ever think of without being told. And so I want to discuss how it could be told. So the problem was this, not exactly this, but was near enough. What is the 10,000th digit of root 2 plus root 3 to the 2017? Okay, so let's assume that we don't have Mathematica or Maple or something to hand. If we do, we'll it'd be slightly disappointing. So you're locked in a room with just a lot of paper and a biro. So how do we solve this problem? So this is, I think, comes into the category of something you just stare at and have no idea, or if you're a computer, you might sort of hopelessly, maybe the. Another disadvantage of just hacking it out on Mathematica is that it's clear, this is one of the first things I'll say, it's clear that the numbers 2017 and 10,000 can't be that important. And so hacking it out, if I just change the question, this is one of the first things I'll do. This is a very sort of standard move, generalize. So one thing you do to generalize, you generalize if you think there are details in the problem that are not likely to be very important. So immediately we'll say, what is the nth digit of root 2 plus root 3 to the m? And then, of course, we will be free later on to impose conditions on n and m that we then need to check are satisfied by 10,000 and 2017. but we'd like to sort of answer this question. So in a state of complete hopelessness, one of the things we do is just say, so now our meta variable has become the proof. We've got a proof. Let's see what we can say about the proof. We don't know what the proof is, but what can we say about it? Well, it's going to have to end somehow with a calculation of the nth digit. And so we could ask ourselves, well, what methods are there for finding, or for calculating the nth digit by hand of when n is very large, or at least that work for some numbers? So when we start thinking, when can, I think I won't write all this down, so I'll just say it verbally. When can we ever work out the sort of 10 billionth digit of something? Well, there are a few examples. If the number is an integer, we can do it. Actually, if the numbers are rational with small denominator, we can do it. So does this look as though it's going to be an integer or a rational with small denominator? No, it's got a sort of rather terrifyingly irrational look about it. So is there anything else we can do? So another thing we might ask is, well, we know how to do it for integers and rationals with the small denominator. Is it conceivable that we can get from what, so this is another thing we do all the time in math, sort of try to move from what you know to something that you don't know. So don't just get from 0 to what you don't know, but get from somewhere sort of a bit closer, sort of get from your first order approximation to what you want to prove. So then if you start thinking along those lines, then another thought is, well, okay, we don't actually need it to be rational or an integer, but it would be enough if it was just very, 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 very close to a rational with small denominator, or very, 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 very close to an integer. If we could prove that, then we'd be in great shape. So we could ask, let's try the simpler of those two things. Let's forget about rational with small denominator, because small is a bit sort of vague, and if it's going to work, then there's probably a fairly good chance that it's going to work with 1. At least it's worth a try. So let's just try. We'll change our target is going to be to show that it's n plus delta, where delta is, sorry, I shouldn't say n. I'll call it x, even though I don't like using x for integers. So it's x plus delta, where x is an integer and delta is smaller than 10 to the minus n or something like that. So that'll. So is there any hope of proving that? Now, this is something that Polya used to say quite a lot, that one very useful technique is generalization, and another very useful technique is making things more specialized. So this m is now, before it seemed a good idea, sort of cut the crap and let's put an m, but now when I'm investigating this general statement, I still don't really know what to do, so I'm going to see what happens if I take m equals 2, let's say. So 1 doesn't seem very helpful, so let's try 2. So what happens if I expand out this when m equals 2? I get 2 plus 3 plus 2 root 2 root 3 should equal x plus delta. So now I have to think, what am I going to take as my x and what am I going to take as my delta? And well, a first look at it might suggest taking x as 5 and delta as minus 2 root 2 root 3, but somehow that delta doesn't look as though it's small in any way, so that's not a very nice thing to choose. Let's just rewrite it as 2 plus 3 equals x plus delta minus 2 root 2 root 3. Sorry, what did I write? I think I may have written something. Ah. Okay, so I'm going to... this is just silly, but the way it comes out more nicely, in a nicer way, if instead of doing it like that, I write this plus delta equals x. So this plus something small equals x. It shouldn't make a difference. Let's just get rid of that. The little story is nicer if I do this. So now we have 2 plus 3 plus 2 root 2 root 3 plus something equals integer. And it doesn't seem to make it nicer. Okay, so I know what I thought. We need to add. So this was the thought process. That's one of the reasons I don't usually use notes. But one of the reasons for using notes is that when you're working out a problem, your brain sort of gets rid of the thought processes very, very quickly. So it's very hard to hold on to them. So I've looked back here and I've seen that I was in a clearer state of mind this morning. So the way I thought about it was. So I keep having to look back at it because it's, oh yes, in order to get an integer, I'm going to have to add, so this is a necessary condition, I'm going to have to add something of the form y minus 2 root 2 root 3. That is a necessary and sufficient condition for this plus this to be an integer. So now the question is, what would make a good choice of y? And here's the point at which there is a rather natural choice. Because this 2 and 3 are floating around, it's sort of quite natural to try y equals 2 plus 3 as well. Because of the sort of full step I've just taken, that's not quite as convincing as it was supposed to be. But anyway, of course we could also have spotted, well, if we take y equals 2 plus 3, this is going to factorize nicely. You might have already seen that in advance. But anyway, so let's just put y equals 2 plus 3. And then we say, aha, right, that's going to give us an integer. And it's closely related to this. It's just got a minus there. This is just an expression for root 2 minus root 3 squared. So we've actually made a nice little observation, which is that root 2 plus root 3 squared plus that equals integer. Of course, that was a natural choice, but we haven't checked that it's small. Is it small? Well, it is sort of, because root 3 and root 2 are only about 0.3 apart. And so their difference is going to be about 1/10. And this power 2 is pretty small. So 1/10, that looks like rather a promising situation. So at this point, having just messed around with 2, it becomes extremely obvious now to sort of conjecture that root 2 plus root 3 to the m plus root 2 minus root 3 to the m equals integer. And while we're writing that down, we spot that root 2 minus root 3 to the m is going to be absolutely tiny. If you try that, you'll see that it's actually false when m is odd. When you take m equals 1, we get 2 root 2. So, but there, if you change that plus to a minus, so what I really should, it turns out if you little bit of experiment, the right conjecture is, no, so it always false when m is, maybe there's nothing we can do when m is odd, but if I took 10,000. So now we'll just add in the extra condition, sort of m even, because it turns out to be useful. I can't be bothered now to check whether it's absolutely necessary to what I'm doing. We're free to do that because 10,000 is even.
But in your original problem, you were down it was 2017.
No.
Maybe that doesn't change.
I wasn't free to do that. Okay. That's very distracting.
Should have been doing it last year.
And in fact, okay, so there's a proof that we cannot possibly hope to solve it for 2017 because we'll get an integer, then we'll multiply it by root 2 plus root 3, and so we'll get a horrible irrational. And we said it could be very close, but I don't think it is. I don't think it'll be close to an integer. All right, so I should have said, exactly, I wish I'd given the talk last year. So actually, even better reason for not hacking it out. We've got an extra insight into the problem. It was false, but, or not false. It was just not the right problem. Anyway, when m is even, we get, when we expand this out, we get nice powers that are sort of even powers of root 2 times even powers of root 3. All those are integers. And then we get nasty ones that involve odd powers of root 2 and odd powers of root 3. And those all cancel out the same ones that come from the second bracket. So we end up with an integer. And then it's easy to check you've got a solution to the whole thing. So again, if you just presented the thing, you wanted to sort of try and convince people that mathematicians are geniuses, you ignore all this stuff and you just say, well, here's what we're going to do. We're going to add root 2 plus root 3, root 2 minus root 3 to the m, observe that it all cancels, and observe that this is small, and therefore, by the way, the answer then is 9, provided m is even and n is reasonably much bigger than m. It sort of needs to be about twice as big as m or something for the proof to work. Because 0.3 squared is less than a tenth. And another thing I just comment about that is that if you know that it's an Olympiad problem, you sort of know there's a trick. So you know that there's going to have to be some sort of magic key that unlocks the problem. But actually, so not all problems are like that, of course. Not all research problems have these sort of little magic keys that unlock the whole problem. But I think they're particularly good examples for talking about the possibilities for fully automatic theorem proving, because finding little magic keys seems like the kind of thing that humans can do that computers can't, and that is what I want to try to argue is not, I mean, is the case at the moment, but will not always be the case. So finally, what about the problem that I tackled this morning? Here I really do need my notes to hand, just to remember what I thought. And I went down some wrong turns, although some of the wrong turns were just stupid wrong turns, as I'll explain in a minute. Just straightforward idiotic mistakes rather than... So the question is the following. Does there exist a subset of the non-negative integers such that for all non-negative integers n, there is a unique pair xy of elements of S, and perhaps I want an ordered pair, yeah, I'll write it like that, such that x plus 2y equals n. So can we find a set S such that everything can be represented in exactly one way as a sum of two, as this linear combination? So here's the warning that I'm pretty sure I've solved this, but I haven't sort of spent ages obsessively checking it, so if it turns out to be wrong, I apologize in advance, but I'm reasonably confident. And there's a follow-up question. What happens if you replace n union 0 by z, just all integers rather than just the non-negative integers? So the process I want to try to talk about now is the process of taking a problem, which is a question, and when you can't, again, it's hopeless to try to sort of guess a set S. You've got uncountably many possibilities. So we don't do that. We ask sub-questions and try to solve those. And we had there's a notion that I, again, sort of little private notion that I have in mind, which is what I call a splitting question. So a splitting question, you start with the question Q. A splitting question is a question Q1, or it's, let's say, a good splitting question is a question Q1 such that Q1 is easier than Q. It's not a formal definition, of course, and that Q, so answering Q1 is easier than answering Q, and answering Q, once you've got the answer to Q1, is easier than Q. So we sort of somehow want to find a question where it should be easier to answer, and answering it should help us. So it mustn't be sort of too close to Q, and it mustn't be too close to 0. It should be somewhere in the middle, and that's why I call it. And of course, once you've got that, you can then try and split again and split the difference. And I feel that mathematicians are doing this a lot of the time. And also, very importantly, we have.
Theorem provers do this all the time.
Oh, right.
It's called an interpolant.
Okay, that's make mental note. Okay, so interpolants are hugely important for to do even fully automatic theorem provers. That's very interesting. I'd be interested to be able to have a pointer to. Well, maybe it's just ubiquitous in the literature, but if there's some sort of good reference for reading up about that, I'd be very interested. But my guess is that what I'm going to talk about is rather high-level interpolants that are beyond what current technology can do. Except also a lot of the ways that I will use the term interpolant now rather than splitting question. I shall try to generate interpolants by sort of reasonably general, standard sort of Polya-ish techniques. So a natural question connected with some of what I've been saying before is, so if S exists, what can we say? By the way, I've been, I should have warned you, but I've been told not to worry too much about the time. This will probably take me another 10 to 15 minutes, so if that's all right, then. I'm going to number my questions in a sort of tree-like way. So what can we say about it? Well, if you're just in the early processes of sort of feeling around, a natural question is, can we say, or can we show, that some n belongs to S? Some particular n, of course. I don't mean that there exists an element of S. We can certainly say that. But can we find of some particular n that it belongs to S? And now I think it's very natural to go for the simplest one. So sub-question of question 1,1 is question 1,1,1. Can we prove that 0 belongs to S? And a quick search, a quick sort of thing is this, of course, 0 belongs to S, because we have to be able to write 0 as a sum of two, this combination of two non-negative integers, and so they both have to be 0. So yes, and we've got our first answer to an interpolant of an interpolant of an interpolant. And now, sort of feel that's telling us something, but it's not telling us absolutely everything we might. So 1,1,2, does 1 belong to S? Well, we can't make 1 using 0 alone. So we're going to have something. If we've got anything bigger than 1, it's not going to help us make 1, so we've got to have 1. And well, when I was doing it, I went a step further. Does 2 belong to S? And the answer is no, because 0 plus 2 1s makes 2, and 2 plus 2 zeros makes 2. So if you put 2 in, we'd have a non-unique representation of 2. And well, what am I doing here? I'm just going greedily through, and each case I'm just saying, does it belong or doesn't it belong? And I seem to be able to prove it one way or the other. So, obvious question now. We don't want to sort of keep on doing this up to 10,000 or something. If we find ourselves in a little loop, we want to break out of it somehow. So we can ask, what happens if I continue this? I don't know whether that's sufficiently formal to count as an interpolant, but probably could be made more formal. But for a human mathematician, that would be a perfectly reasonable one, I think. So when I was thinking about it, I suddenly thought,
Sorry.
is there any alternative actually to this greedy approach? So I was forced to put in 0, I was forced to put in 1, I was forced not to put in 2. Am I actually always going to be forced when I've got to? If I've worked out for all the numbers up to n whether or not they're in, is it conceivable that I could have a choice about what to do with n plus 1? And once I'd had that thought, well, I'll just say no. Let me quickly explain why there's no alternative. It's because if you know for all the numbers 1 up to n whether they're in, if you can already make n plus 1, you can't put n plus 1 in because you could have n plus 1 plus 2 zeros. If you can't already make n plus 1, obviously you have to put n plus 1 in, and then it'll be n plus 1 plus 2 zeros. So actually the greedy algorithm is, there's a unique, we now already know there's a unique set if there's a set. So at that point I thought, right, let's just blast away. I somehow believed, because it went for n as a non-negative first and z second, I was sort of believing that it was probably false for the non-negatives and true for z. So I thought, best way of finding a counterexample, just pursue this greedy algorithm until I get some contradiction. And I did so, and I'll spare you the gory details. I went from 0, 1, 3, 8, 9, 12. No, sorry, I went 0, 1, 3, 4, 13, 14, 17, 18, and then I got that 26 has 2 representations, and all this was forced. Now you will have noticed if you learned, that was a mistake. Yes, this is what I said. I warned you there was some idiocy in advance. So I corrected this and made another mistake. So I managed to convince myself that it was false twice, wrongly. When I finally did it more carefully, this is what happened. So I went for 0, 1. Okay, now let's just talk you through this. 2 is 0 plus 2 1s. 3 is 1 plus 2 1s. 4 is the first one that we can't produce. 5 we can't produce because 4 plus an even number is all we can really hope for there. And now we can get a lot of things. So 6 is 4 plus 2 1s. 7 is 5 plus 2 1s. 8 is 0 plus 2 4s. 9 is 1 plus 2 4s. 10 is 0 plus 2 5s. 11 is 1 plus 2 5s. 12 is 4 plus 2 4s. 13 is 5 plus 2 4s. 14 is 4 plus 2 5s. 15 is 5 plus 2 5s. 16 is obviously bigger than everything because 5 plus 2 5s is the biggest you can do. So it's 16. And then, okay, 17. And at this point I was really hoping that I'd get a gap of 3. And I did get a gap of 3. So an obvious question now is there a pattern emerging here? And now I suppose I'm going to exploit my sort of human ability to spot patterns a little bit, but I don't think that this particular bit of pattern spotting is necessarily way beyond, sort of way out of reach. Which is when I see something like this, it's starting to look sort of Cantor set-like, or sort of product of lots of things. And actually, Cantor sets sort of structures seem like the kinds of ones you want because what is the density of S going to be like up to n? It should be about root n because you've got sort of, when you've got m things, you have roughly m squared. In fact, you've got exactly m squared ways of making x plus 2y if x and y both come from a set of size s and are allowed to be the same. So one way of constructing Cantor-like sets is to take sets such that all the digits take certain values, base something or other. And my initial thought was, oh yes, so perhaps everything here, perhaps we take all numbers that are 0, 1, 4, or 5, base 16. And you can check that that works because 0, 1, 4, and 5 get you all the way up to 15. And then when you're sort of taking bigger and bigger Cartesian products of this set, so to speak, you're getting more and more numbers. But then I thought, this looks as though I'm making a mountain out of a molehill here, and then I realized I was. It's all numbers that in base 4 have just the digits 0 or 1. But I have to, honesty compels me to say that I went through that stupid step first. But I did have a sort of instinct that maybe it would be simpler. So I won't give this because I just want to show where the ideas came from. Checking that all numbers that have digits 0 or 1 mod 4, that example works, is easy. And I've sort of given you the proof. So you can, from 0 and 1 you can get 0, 1, 2 and 3. And then the same thing just happens in every single digit, basically. Okay. So what about... Oh, I should say that, yes, I moved on to Z, having satisfied myself that it was false for this, and I only sort of realized my mistake after sort of thinking about the Z case and coming up to with certain realizations that contradicted what I'd seen before. So having proved that it was yes for this, I immediately thought, okay, it's going to be false for Z. But for Z, it's not nearly, I did some experimenting, and this sort of orderly sequence of interpolants, each one being clear what it's an interpolant of, it broke down after a while because ideas started sort of popping into my head. So now I'll just describe in a looser way how the rest of the thing worked. So I started to believe that the answer for Z was no, and I wanted to find some kind of reason. Couldn't see a reason, but then I could thought, well, maybe I'll try to prove at least that if you go for all the digits being certain values base m, perhaps that class of examples can't work for Z. Then I sort of thought, well, actually, I don't quite know what it means to take the digits base m of a negative integer. What is the base 2 representation of -1? We seem to need the minus sign in front of it. But then I remembered that you can do nice things base 3 if you just have you can have digits of 1, 0 and -1 base 3. So if you can write every integer in a unique form as a linear combination of powers of 3 where the coefficients are 1, 0 or -1. And I sort of filed that away. But then I thought, okay, so supposing you could find a base and some set such that, so we find a base m and some set a such as you can write every integer as a sum of powers of m with coefficients in a, point number 1, and suppose that a, you can represent everything in a uniquely as x plus 2y for x and y belonging to some other subset b, let's say, then we'll be done. That'll be because then you can sort of do a digit by digit approach just as in the first case. Okay, because I'm short of time, I think I'll just sort of jump a little bit. So having thought about the base 3 thing, that was actually very helpful, because how do you get to this representation of base 3? You just take the normal ternary representation with digits 0, 1, 2, and you just shift it to -1, 0 and 1. Then it suddenly occurred to me, not immediately, but after a little bit, it occurred to me that perhaps we could do some, well, there was a problem. What about this? We've got something here where that does exactly what we want, base 4, and so it's tempting to take these two numbers and just shift those. But if I shift those, I get from 0, 1 to -1, 0, and then I end up getting all the positive numbers to getting all the negative numbers, and that doesn't really help. So then I thought that's a problem. So maybe there's some reason, and I tried base 9 for a bit. So then there was a moment of, I don't want to say inspiration, because it sort of bubbled up after trying 9 and it failed. I sort of realized going back to that base 16 thing that was sort of stupid, it turned out to be very useful, because if I shift 0, 1, 4, 5 back a little bit, let's say to -2, -1, 2 and 3, and consider what numbers I can get. Well, first of all, what number can I make out of those? Well, because I've moved everything back by 2, whereas before out of 0, 1, 4, 5 I could get everything up to 15. Now I can get everything from -8 up to 7 or something like that. Actually, I think I went from -1 up to, it's not -8, it's -6 up to 9. So -2 plus 2 minus 2 is all the way up to 3 plus 2 3s. Because I've just translated everything, I'm still going to get instead of getting the numbers from 0 to 15, I get all the numbers from -6 up to 9. So now I just left needing to prove that every integer has a unique representation as a sum of powers of 16 with coefficients in this set from -6 to 9, which turned out to be an easy thing, or easy-ish thing to check. There was an additional little sort of element of the checking process, but it is genuinely an exercise. So out of, there was a thought process that again you could present it as saying, consider the set of all integers that can be written as linear combinations of powers of 16 with coefficients in this set, and then you prove that you can make every integer out of out of adding one of those and two of another. And then it would look like some flash of inspiration, but actually the process that led to this example. So there were some bits, I confess, that the way I've presented it look as though they slightly came from that sort of recognizing the Cantor set. But the principle I have when thinking about these examples is, if you start with a sort of mega inspiration that's needed, if you can reduce that to a series of smaller inspirations, then by induction you're done. So that's sort of my attitude here. So if there may be more explanation that's necessary, but it's lower level explanation. And now I think I've probably outstayed my welcome, so I will stop.
Questions? So I'll ask one. This problem actually, it looks like if you used a bit vector representation, then you could figure out that you could get all the 4-bit ones from 0, 1, 4, and 5, and that then it's a repeating pattern because multiplying by 2 is just a shift left.
I see what you mean. Yes, yes.
So then
that's a nicer way of, much nicer way of looking at it.
And maybe the 2's complement representation for integers might help with the integers then. So in 2's complements, you put the negative numbers above the positive numbers. So it's 0 to 2 to the n minus 1 minus 1, and then the negative numbers start from the least negative number upwards. So that might be a way of.
I think the issue with using 2's complement in this context.
There's the end around, so it doesn't actually, the shift left doesn't work as well.
Well, you would have to have an infinite number of, as a formal combination, right. you end up adding infinitely many, which you can't really, since here you have to have elements of the set which you're adding together, it's not clear how to interpret those negative elements.
Yeah, so maybe this, the linear combination might be a better solution. Yeah, Andy?
Thinking in the very long term, I suppose. What about, what are the prospects for sort of machines doing theory construction? In other words, pretty crudely making up the concept of a group, as it were, as a step towards solving a problem.
Well, I don't think that is often put forward as something that's sort of very particularly human and requires imagination.
Necessarily.
No, so I mean, one reason that groups get formed and other algebraic structures is that you just find you're dealing with concrete groups a lot, and after a while you spot that you're only using certain properties of those, and you then sort of just, there is a process of abstraction which we're all familiar with, and you say, well, let's take those properties that are the ones I'm using. We do it all the time when solving problems anyway, so you've got some concrete structure that you want to prove something about. You try not to use, or often you try not to use the actual definition of the structure. You try to prove that it's got some properties and then use those properties to solve something. So if you've got a lot of problems and the same properties keep showing up, then it's a sort of natural thing to develop a theory. So for maybe that's a bit of a glib answer for the entirety of mathematical theory, but I think it shows at least that in principle, some theory can be developed. And a similar thing.
I suppose that there's no guarantee, of course, that the theories that the machines come up with would be ones that we'd like.
Well, I was about to say also, so that's something else that people say, machines will not be able to tell what's interesting and what's not. But I think if you just look at what human mathematicians do, one small remark is that not everything that's produced by human mathematicians. That's not. But a more important remark is that somehow something's interesting if it's motivated, and it's motivated if, I think, roughly speaking, if it's an interpolant for something that's recognized as important, or an interpolant of an interpolant. The beginning of a paper will say, it is a long-term goal of my area to do blah, 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 and, one thing that would be nice to know more about is this, and if we could just do this, and then finally, after a few stages of this, you get down to our main theorem does such and such. And so I think quite a lot of the way conjectures get formed in mathematics is that you're doing some fairly straightforward reasoning, and then you find yourself with a piece of data, and this is the thing you want to prove, and you get stuck. And it wasn't the thing you originally tried to prove, but it's something new that's done after a process of reasoning, and it's quite a nice statement often, but where you're stuck, and there isn't an obvious counterexample. And at that point, it's sort of natural to make it a conjecture, and it's sort of interesting because it's motivated by the thing that you were first trying to do. I think that sort of process happens an awful lot in real mathematics, and so again, that makes me optimistic that a well-programmed computer would be able to have some mathematical taste, as well as it wouldn't just be sort of churning out more and more theorems that were of no interest to anyone.
It's not just, I think, theory formation. I mean, there's also kind of, or what is interesting, and what is worth pursuing. There's, as humans, mathematicians see analogies and similarities, and they think, oh, if I could do that construction, I should be able to do this construction by similar means. And the example that came up of Andrew Wiles's proof, actually, in the text, he says, there's a lot of similarities, and so on, in the proof itself. And this kind of gives you a heuristic for what directions are promising.
Yes, that's something that I haven't thought about in the sense of thought about how to try to automate, but it's clearly, I mean, in my own research life, this is what I do the whole time. I sort of recently, a recent result was of exactly that structure. So I wanted to prove something when a particular parameter equaled 4, and there was a known proof when that parameter equaled 3 that had lots of steps, and so it was natural just to say, let's take each step and try to generalize it, and then it turned out not to be possible to do in an easy way, but this is again often happens, you try to sort of modify the steps of the known case to make them more amenable to generalization, and that was possible, and eventually out came a result like that. And I mean, that's another example actually of the sort of principle that I alluded to earlier, of sort of start with what you know and then move to what you want, rather than start from 0 and move to what you want. Well, it's a much higher level example of that than what I was talking about earlier. And it would be, I think that ought to be, at least up to a certain point, that also many examples of that ought to be possible to automate by a process such as taking statements and sort of making them less precise. So instead of saying, I've got these vectors are independent in the vector space, you might want to say these objects are independent in some structure, and then the definition of independence would be something like whenever you take a combination, and not necessarily linear combination, but a combination, or any two combinations are different, or something like that, and then that would sort of slightly relate what was going on here with
this is where I think formalization helps, in that some of these patterns are the abstractions are actually at the level of the syntax.
Yes, exactly. I think sometimes two things are analogous simply because at some vaguer level they are actually identical, rather than so. If that, I mean, there are definitely examples where that's the case. And if that, I mean, whenever that is the case, you can imagine just a vaguification process, and then a sort of just searching for matches. And there are probably sort of more subtle analogies that are not so easy to do, but I think you could get a long way with that sort of idea.
There's again a term for that, anti-unification. Oh, right. Is the term that you use for common generalization of things.
So what I'm thinking of is
finding the most general common instance, and anti-unification is finding the.
So is anti-unification allowed to be an imprecise statement?
Yeah,
it is. Okay. In that case,
I'm not sure, because you are still on the symbolic level. Whereas, for example, when you take some neural representation, it's much more imprecise in some sense. Like in anti-unification, you are still saying like this has a very exact symbolic meaning, right? Whereas you can do this much more fuzzy by using other methods.
What else?
Oh, like embeddings, for example, doing some sort of neural representation which creates a high-dimensional vector out of your piece of formula, and then just measuring the distances in that that's basically what linguists do
True, yeah,
today.
that's right. Yeah, that's even you can make that even less precise. Yeah. Let's see, someone else. Yeah, Mario Paulo. Yeah.
I appreciate very much the optimism that you have for improving. So I really loved it. I find it very interesting because so many of the ideas that you have mentioned have been tried in the automated theory improving community, but all of them today are still very much in a state of infancy.
yeah.
I mean, backward reasoning has been tried a lot, and one thing that is backward reasoning from the goal, has been tried a lot. And one thing that has baffled people for many years in automated theory improving is that there were always high expectations about reasoning from the goal, but machine's method seems to be better off reasoning forward rather than backward, and we still don't know why that is the case. One possibility is that often when comparing human performance and machine performance, the machine is somehow required to start from basic principles, whereas the human reasoner has a lot of background that is difficult to encode in the machine. And when we try to bring in very large knowledge bases with lots of formulae that are supposed to encode all the background knowledge that the human reasoner has, the problem is that all these formulae are seen by the machine in a sort of flat way because there is no judgment to pick them, and therefore this only makes the search problem in a sense even worse because there are all these initial axioms to use. But many of the ideas that you've touched upon, like combining forward and backward, for example, having one strategy generate dilemmas for another, and so on, have been tried. I only think that they've been tried to a very short extent. So I think that we need to do much more work on many of those in order to achieve progress. Sometimes I feel that in our field, it's like people get discouraged too quickly. You know, they try something with high expectations, it doesn't work, and then they just set it aside. But it really requires a lot of persistence to get some of these strategies to work.
Yes, maybe I could just say, but having set out with having sort of had this experience with Mohan Gnanasamlingam of setting out with very high expectations and ending up with a program that could only solve rather modest, easy problems. So why didn't I end up discouraged by that? It's because what was stopping us didn't feel like fundamental reasons. It felt like just small technical difficulties that if only we had one more big push, which I haven't had time to do over the last couple of years because I've been thinking about sort of my more purely mathematical research a bit more. Finally I'd get past this hurdle and into the promised land where suddenly the pace of progress would speed up. I still confess to having that feeling. Even though, although I would totally understand if other people feel sort of more skeptical about it, and that's a very reasonable response. But I just
one of my professors, Edgar Dijkstra, was really he would have teach entire courses on what's called mathematical methodology. so that you could avoid pulling rabbits out of a hat. He would tell you, how you could actually introspect about your thought process, so that you knew why you did what you did, and everything had a kind, almost like it was deterministic. This is what you had to do in this situation. And so, I mean, he has actually, I think, developed a number of heuristics for doing this. He's passed away, but his writings are still there, and I think there's a website with what are called EWDs. And he has, I think, an unfinished draft of a book called Mathematical Methodology for doing this.
I'd love to see that.
Yeah. But one of the things that happens in this is it kind of takes the romance out of mathematics. Pulling rabbits out of a hat is, what makes us feel good. We think, oh, this was something.
Yeah, actually, on that sociological point, I've always been a bit of an anti-romantic in that sense, because I think of course, it makes us feel good, but it also, I think, puts off. It makes it hard for people to come into the subject, because they see these experts who pull rabbits out of their hat all the time, and they think, oh, I could never do that. And so I'm sort of keen to counter that view and show that it can be done, and it's not a sort of, once you look under the hood, there is actually something.
You have a question?
So I sort of, you said that you are striving for a well-programmed system, and if you invest enough energy, it will come. So I'm just
saying that's the feeling I have in some kind of immersion.
I think that this is a feeling which various people had, and I would say one of the lessons which AI researchers learned is that it plateaus at some point. Like for example, Leonard was reasonably successful with artificial mathematician, or automated mathematician, and then he did Euroscope.
This was a program that essentially generated conjectures based on heuristic.
And basically then he wrote a paper why Euroscope failed, and then he set about to do this side project where he would encode all of human common sense knowledge. And I was talking with the people, with the CTO and CEO like 10 years ago, and I told them that I'm doing machine learning rather than encoding it myself. And that they said, yes, this is what we should be doing, because the complexity kills them at some point. Like you have so many rules and so many theories and so many ways how to combine them in particular combination of theories, that the human can basically no longer engineer that. And I think the answer which AI has today for this is to learn it from sufficient amount of data, like your traces of mathematical Olympiad solutions, for example. And I agree that sort of has to be designed so that the learning is done on a reasonably high level way, rather than
so you couldn't just feed it solutions to Olympiad problems and hope that it'll generate anything other than gibberish, I think.
Well,
if you give it all the corpus of Olympiad problems that's ever been in any country, together with very nicely written out solutions, and then gave it a new Olympiad problem,
so
any sort of neural network, it might produce something that looks vaguely like a mathematical sentence, but...
I'm not talking about neural nets, but 20 years ago, there are these systems which do anti-unification. It's called inductive logic programming, for example. So there are many non-statistical ways of doing learning from data, like when you can really learn the rules and symbolic knowledge.
So I think if instead you had a program that was slightly non-deterministic, that did these kinds of reasoning, and you made it non-deterministic in the situations where you couldn't, as a programmer, work out what the right step would be, then I think machine learning could sort of come in and look at, that's the sort of situation where I think it may well have an important role.
What would be needed for it, and people are, like Joe Connelly is now looking, for example, at math overflow, is really not just the solutions where you come with the rabbit, but really some sort of thought process like you described. So unfortunately, we typically don't have that, right? So maybe math overflow is the best that we have currently for getting a corpus like that, for doing something like that.
Yeah, I've produced a few myself, not all of which I've made sort of made public, but I think I will, because somewhere I've tried to do again a sequence of interpolants that sort of gets you right down to a sort of low level, and then when you solve that one, it sort of feeds up and you build back up the tree and so on, with some quite complicated problems.
Do you think that the polymath project is a very good process for this?
Well, if suitably translated into something that a machine could analyze, then quite possibly. I mean, there's a lot of noise in a typical polymath discussion. I'm thinking of things that I had been going to say, but I think it's a sort of change of subject.
Actually, you've touched on many of the themes that were in not just the workshop, but in many of the talks. And as Maria Paula mentioned, some of these things, people have been pursuing both within automated reasoning as well as AI in general. And if you look back, for example, at the Newell-Simon work on...
I'm aware that this would be slightly disparaged as kind of good old-fashioned AI, rather than...
I think,
but I sort of feel that it's due a revival.
I don't think these ideas go out of fashion at all. I think, so in Newell-Simon's work, they had this general problem solver with means-ends analysis. They even had this idea of actually doing what's called protocol analysis. They would sit down and actually verbalize exactly everything that they thought about in solving the problem.
What with a tape recorder running?
Things that didn't work out, and they would actually record all this just so that they could try and program these tricks into the system they were building, this GPS system. But I think with in certainly the next 50 years, with the technology available, we can take a deeper look at some of these ideas. And
I think some happy marriage of the old-fashioned approach with more modern approaches, I think, have a lot of potential.
But I think the going through some of these problems in greater detail and actually seeing how one might automate the patterns that emerge in this, the heuristics that seem to drive you towards certain things, the connections that you would make with the background knowledge that you have, not just syntactically, but in this kind of vagueness notion that this looks a lot like that, would be, I think, worth pursuing in the next 50 years of the research in the field. So with that, thanks a lot, and we wish you a great year in Paris.